Okay, Algebra 2, we're going to get working on section 5.2 here, and we're going to try to keep this one relatively short, although we do have some slides and a decent amount of stuff to go through. So moving on into section 5.2 here, we're going to start talking about the connection between a lot of different words that are going to get thrown at you here. When we're talking about polynomials, when we factor a polynomial and we find something called zeros, those things are all kind of connected here. And we're going to use that to go a little bit further and what we just dabbled in a little bit in 5.1, which was graphing complex polynomial functions. And we're going to try to get a little bit more specific with it here in 5.2. So the first thing I wanted to do with you guys is just have a real quick review of factoring here in some higher order polynomials. Most of the factoring that we did back in chapter 4 was really just with quadratic functions. But I wanted to talk about what to do if you ever see a cubic function or something higher like what we see right here. And I just wanted to do one quick example with you. We'll get more practice at this during the course of this section. But if they were to ask you to factor, in this case, a cubic trinomial, regardless of how complex that function is, the first thing you always want to do is look for a GCF. And so as we're looking here at 6x cubed and a 21x squared and a minus 12x, it looks like we can pull a 3 out from each of those three terms right there. Let's try that again. A 3, and with an x cubed and an x squared and an x, we can pull out an x as well. So that 3x is our GCF, and we start then a set of parentheses, dividing the 3x out from each of the three individual terms. So with 6 dividing by 3, we're left with a 2. There were 3 x's, and we pulled out 1. That leaves 2 of them. On to the second term now. There was a 21. We divided out a 3, so that leaves us with a 7. And there were 2 x's. We pulled out 1, so that leaves 1 x behind. And for the last term now, 12 divided by the 3 we pulled out leaves us with a 4. And there was 1x, but we pulled it out, so there's no x's left in the parentheses. So what we've done right now is we've pulled out just a greatest common factor. But we're not done, because in all likelihood, the trinomial that's left over can be factored as well. What's important, though, guys, is that the 3x doesn't disappear. It stays here as part of our final answer. And now, I don't see a difference of squares here. I don't think we see a perfect square trinomial. We're going to try what I consider to be normal factoring, which is really reverse FOIL. What times what is going to give us 2x squared? Well, that's going to be a 2x here, and then just a 1x right over here. By looking at this minus sign right over there, I know that these two signs now are going to have to be negative. 1 plus and 1 minus. Now I don't know, need to be opposites. 1 plus and 1 minus. Now I don't know which one is which, so I just take a guess. And now we're looking for two numbers here that multiply to 4. And don't worry about them adding up to 7 yet, because that 2 right there kind of complicates some things. So if we were going to pick two numbers that multiplied to 4, my first guess would be 2 and 2, but I'm pretty sure this one doesn't work. Let's check it. The outer product there would be a negative 4x, and the inner product would be a positive 2x. That makes a negative 2x, and we needed a positive 7x. Nope. That didn't do it. 2 and 2 didn't work, and switching those numbers wouldn't work because they're the same number. So it's probably going to be 4 and 1 as the only other possibility for how to split up the 4 other than 2 and 1. And I don't think this one works either. 2x times negative 1 is negative 2x. 4 times x is 4x. That makes a positive 2x. Not the 7x that we needed. So 4 and 1 didn't work. Let's try switching those numbers to a 1 here and a 4 here, and now we're getting closer. 2x times a negative 4 is a negative 8x. 1 times x is 1x. Negative 8x plus x is negative 7x. We needed a positive 7x. So when you're that close, guys, that just means that you got your signs backwards. So instead of plus minus, we're going to switch this one around a little bit and make it a minus and a plus, and that's going to do what we needed it to do. The 2x times 4 is going to be an 8x. Right there. The negative 1 times x in the middle is a minus x, and that gets you the plus 7x that you needed. So this, everybody, is the fully factored form of this original polynomial expression right here. So we did some of that back in chapter 4, just a little refresher on how that works. Now, this next slide, I don't want you guys to feel like you need to be too worried here about what it is that you're seeing. There is a lot going on in this slide right here, but the important thing is really just a few key words here. So let's try to narrow this down to just what we need. These three words here, guys, roots, zeros, and x-intercepts. For our purposes here today, those are really interchangeable. This is kind of the generic way that your textbook likes to define a polynomial function. They're calling it p of x because it's a polynomial. You've got a, which is a coefficient, like 3 or -7, multiplied by your variable x raised to some power. And to be a polynomial, x has to be an integer. Actually, x has to be positive. So the n there, the exponent could be 3, or it could be 7, or it could even be something small like 1 or 2. Then we're going to add a second term to that with a new unrelated coefficient called b, the same variable now x, but the power goes down by 1. So if we started right here with a fourth power, we would now be at a third power. Then there's another term that you could potentially add to it. C is your new coefficient, same variable x, and now the power goes down again. So if we had a 4, this would be a third power, and this would be a second. Then this is getting kind of tedious, so we do a plus, and the ... means go on as long as you need to, but then we end this thing with a plus k. And you'll notice there's no x's there, so that k is meant to represent the constant that comes at the end of a polynomial function. And if that's how we define our polynomial, all of the following statements are equivalent, and we've got 4 of them here. The first one, x minus q is what we call a linear factor of that polynomial function, p of x. So if we go back to the problem we were just working on, this might be your p of x function right here. And then each of these, each of these, 3x, 2x minus 1, and x plus 4 would all be considered linear factors of that original polynomial. So that's why factoring is really important. But actually, this explains it even more. The second one right here, it says that if q is a 0 of the polynomial function, which means that the polynomial evaluated at that q value is equal to 0, that comes from this same number that we just found here by factoring. Don't worry about that. We'll explore that a little bit more. It's also equivalent to saying that q is a root or a solution of the polynomial equation p of x is equal to 0. So we can use factoring to find solutions to polynomial equations. We know that because we did that back in chapter 4. And then this last one graphically here, q, the number that we're dealing with here, the solution to your polynomial equation, q is also an x-intercept of the graph y equals p of x. Okay, so I know that's confusing, that's a lot of vocab, but basically what we need to know here is that roots and zeros and x-intercepts are all pretty much the same thing. Not exactly, but that's more semantic and it's in terms of vocab, so let's not worry too much about that. So let's get into the types of problems we're actually going to have to solve here in section 5.2. This problem asks us to find the zeros of p of x and then graph this thing. Well, if we went back and looked here, guys, zeros, which it talks about right here in line 2, q is a 0 of p of x if x minus q is a linear factor of p of x. So as we look at this example right here, p of x is given to us, and it's already given to us, you guys, in factored form. So each one of these zeros that we're going to look for comes from taking a linear factor, such as x plus 5, setting it equal to 0, and solving. This one's going to go pretty quickly, and we did this back in chapter 4, so I'm hoping it looks familiar. We're just going to subtract a 5 from each side, and we get one of our zeros here of x equals -5, and I'm going to put a box around that. We have another 0 that's going to come from the linear factor x plus 1. We'll set that equal to 0. We'll subtract a 1 from each side. Those cancel. And we'll get another 0 here of x equals -1. So there's a second 0. And the third one comes from this third linear factor that we have in this case, x minus 3 equals 0. And here we'll add a 3 to both sides. Those will cancel, and we will get x equals 3. So this should look kind of familiar, guys, when you think back to what we did in Chapter 4. The difference being in Chapter 4, everything was quadratic, so we only had 2 solutions. But now we are dealing with higher order polynomial functions. So this is an example of one that has 3. So for finding the zeros of p of x, that's what we've done on this line right here. X equals 5. Negative 5, or x equals negative 1, or x is equal to 3. But they also asked us now to graph this polynomial function. So we can be just a little bit more specific right here, guys, than we were earlier in the previous section of 5.1. So let me go to, let's just make ourselves a quick little graph right here. It doesn't have to be anything fancy here. So we have a y-axis and an x-axis. And what we're going to try to do now is focus on 2 key ideas. The first of which is that the zeros that we just found are, if I go back to page 2 here, your zeros right here are your x-intercepts. It's where your graph crosses the x-axis. So back to this graph here, we know that this graph is going to cross the x-axis 3 times. Once at negative 5, once at negative 1, and once at positive 3. So let me switch back to blue. We'll go with this one right here. We have a 0 at negative 5, which means that is an x-intercept, and we know that our graph passes through that point. We have a second 0 or x-intercept at negative 1 right over here, and a third and final 0 or x-intercept at 3. So we know that this graph has to cross the x-axis at these 3 points. Now the second thing we need to consider in trying to determine what the shape of this polynomial graph is going to look like is what our end behavior is going to be. And for end behavior, what we're going to do, relax, this isn't going to be that bad. We're going to just think about what would happen if you multiplied the first term here times the first term here times the first term here. We're not actually going to multiply all of this out, but x times x times x would give us an x cubed. And then there'd be a bunch of stuff that comes after that, but for end behavior, we're really not interested in that at all. So if we were to think about end behavior the way we were doing back in section 5.1, what we have to do is think about what happens as this term right here, guys, the x cubed, gets replaced with a big negative number, and then what happens when it gets replaced with a positive number. Let's do the left end behavior first. You're going to be putting a negative value in for this x and cubing it. And a negative value to an odd power such as 3, negative times negative times negative, will be negative. And there's no negative coefficient to flip this thing. So putting in a negative right here is going to get us a negative result. That means that as x moves out to the left, our y value is going to approach negative infinity. So this thing is going down on the left. Now let's think about what happens on the right. As we put a positive value here for x, a positive number cubed is going to be positive. And there's nothing weird that happens to flip it. So as x moves out towards positive infinity, our y value approaches positive infinity as well. So we know, just through a real quick bit of analysis right here, that this graph is going to go down on the left and up on the right. And I can use that right now to tell me where to go. From this point right here, everybody, we know that this graph has to go down on the left. And from the point all the way on the right, the x-intercept that we came up with right here, we know that this graph has to go up on the right. Down on the left, up on the right. And now it's really just a matter of connecting the dots, everybody. We're going to go from this x-intercept, make a little hump, and then come back to that x-intercept. And then from point B to point C, we're going to do something like that. And that, you guys, is a pretty decent estimation here for what this graph looks like. So putting that all together, we found the zeros of our polynomial, x equals, x equals negative 5, and x equals negative 1, and x equals positive 3, and we used those as our x-intercepts, and then we used our end behavior right here to come up with this rough sketch for the graph of what p of x looks like in this particular example. Okay, so hopefully that one's not too bad. Now, let's move on to this one right over here. This is a different style of question now, so we're shifting gears a little bit. They are now giving us here, everybody, they're giving us the zeros of a polynomial function, and they're asking us to come up with the function itself in standard form. So this is the exact opposite of the problem that we just did. In this example, they gave you the function, and they wanted us to come up with the zeros. Here, they're giving you the zeros, and they want us to come up with the function. Okay, so our polynomial function, p of x, has 3 zeros. Now, that already tells me something important. That tells me that with, I broke it. All right, that tells me now that with 3 zeros right here, everybody, we know that our degree of this polynomial function is going to equal 3. We're dealing with a cubic function. Now, each one of those zeros, everybody, is going to give us a linear factor of this polynomial function. So with 3 as one of the zeros, x minus 3 is going to be our first linear factor. It's always x minus whatever that number is right there. So moving on, we have a second zero of -1. So our next factor is going to be x minus that number right there. But minus -1, we're going to go ahead and write that as a +1. And then the third zero of 4 is going to give us another linear factor now of x minus 4. And that's what this polynomial function looks like in factored form. Unfortunately for us, they wanted it in standard form. So what we're going to have to do, and I know you guys aren't going to love this, we're going to have to multiply all of this out. And for a reason you might see in a minute, I'm going to multiply with FOIL the second and the third factors together first. So I'm going to leave the x minus 3 here for just a moment, although I'll deal with it soon, and now we're going to do FOIL. First, x times x is going to give us x squared. The outer product is an x times a -4, so that's minus 4x. And then the inner product of +1 times x is 1x. So a -4x plus x is going to be a -3x for the middle term. And then the last product is +1 times -4. That'll be a -4 at the end. So we FOILed the second and the third linear factors. Now we have to do something that I'm not sure we've done yet this year. We're going to multiply out a binomial times a trinomial. FOIL doesn't work for that. So the way we're going to handle this, guys, is what's called the double distributive property. I'm going to take this x right here, and I'm going to distribute that x to all 3 terms here that we're going to get from that trinomial. So let's see what that gets us. The x times x squared is going to be an x cubed. Actually, you know what? I'm going to do that in red for a reason I think you'll see in a minute. All right, so the x times x squared was x cubed. X times a minus 3x is a minus 3x squared. And then the x times the -4 at the end is a minus 4x. We're halfway home, everybody. Now what I'm going to do is I'm going to switch to green. And now we're going to take the second term of this binomial, which is -3. Don't lose that negative. And I'm going to distribute that -3 to the 3 terms in the trinomial as well. So the -3 times x squared is a -3x squared. And I'm going to write that not here, you guys, although I certainly could, but I think it's going to make more sense if I move that right here and I write it underneath the existing x squared term. You'll see why, I think, in a second. Now, what's -3 times -3x? That's a plus 9x. So that'll go right here. And lastly, -3 times -4 is a plus 12. That's the first constant that we've gotten in here. Okay, so now we have multiplied out. We've done kind of the double distributive property. Now all we have to do is put it all together. And the reason I put the green terms under the red terms, I think you guys can see that we're just adding like terms. The x cubed doesn't get added to anything, so it just stays the same. But here, -3x squared minus 3x squared is a minus 6x squared. And right here, negative 4x plus 9x is a plus 5x. And then nothing gets combined with the positive 12. And this, everybody, is the standard form version of the polynomial function. And I should probably say the simplest polynomial function out there that has zeros of 3 and negative 1 and positive 4. So that's what that one looks like. Okay, probably need a little bit more practice with that because there's something a little bit tricky that can happen when things get a little bit more complicated. So let's try the same thing again and see if we can get this one to work. Okay, so p of x is equal to, and here we go. With a 0 of 2, our first linear factor is x minus 2. It's always x minus whatever that 0 was. The next 0 is negative 2, so this would be x minus negative 2, which becomes a plus 2. Then we have a 5, so our third linear factor is x minus 5, and lastly a 3, and we're going to get x minus 3. So that's the factored form. Now for this one, a little bit more complicated because we have 4 linear factors. So we're going to go ahead and multiply these two together and these two together at the same time. Now the nice thing here, that was not what I meant to do, the nice thing here about this problem is that the x minus 2 and the x plus 2 are conjugate binomials. When you FOIL this, the x times x is going to give you x squared. The outer product is going to be a plus 2x. The inner product is a minus 2x. They just cancel each other out. And then the minus 2 times the plus 2 is a minus 4. So it's unusual. But when you FOIL two conjugate binomials, you don't get a trinomial, you get just a binomial. But now let's work on the second one here. I don't think we're going to have any such luck right here. X times x is going to be x squared. Got it. All right. Then outer product, x times minus 3 is minus 3x. Inner product is minus 5x. So that makes a minus 8x. And then the last product, negative 5 times negative 3 is a plus 15. Okay, so we're done with the initial FOIL, everybody, but now we've got to take each term from this binomial and distribute it, kind of long-range distribution, into the trinomial. So here goes. X squared times x squared, we add our exponents together, that's x to the 4th. X squared times a minus 8x is going to be a minus 8x cubed. And then an x squared times a plus 15 is a plus 15x squared. And now I'm going to switch here to green, and we're going to distribute the negative 4. Again, don't forget that negative. That's really important. Negative 4 times x squared is a negative 4x squared, and I'm going to put that here underneath the x squared term. Negative 4 times negative 8x is a plus 32x. I don't have any x terms yet, so I guess that just goes out here by itself. And then negative 4 times 15 is a minus 60. And since there were no constants, that goes on its own too. And now, guys, I think we're just about done. Our polynomial function in standard form, we just add down. X to the 4th doesn't combine with anything, nor does the, that's an ugly 4 I wrote there. Let's try that again. X to the 4th, better. Neither does the minus 8x cubed, but these two terms in the middle will combine. That's going to give us a plus 11x squared. And then the last ones don't combine either. Plus a 32x and a minus 60. And that, everybody, is the simplest, most direct polynomial function we can write that has these 4 zeros of 2, negative 2, 5, and 3. Okay, so moving on from there, everybody. Next, we're going to talk about this weird word here called multiplicity. And the multiplicity of a 0 is essentially the number of times that a 0 or a linear factor can occur within one given polynomial. And something cool happens with multiplicity. This case right here is the one that happens more often. But when you have, here you go. When you have an odd multiplicity, a multiplicity of 1 or 3 or 5, your graph crosses the x-axis at that spot. But, and this doesn't happen as often, when you get an even multiplicity, which is usually 2, but it could be 4 or 6 or 28, the graph bounces off the x-axis, but it doesn't cross at that particular point. So let me show you what that looks like, guys. So in this example, we're being asked to find the multiplicity, and of course we're going to use the multiplicity, and then we're going to try to come up with a graph here. So in this example, f of x is given to us in factored form already, and we've got a linear factor of x, a linear factor of x minus 2, and then this is interesting. The x minus 1 is actually squared. So what that really means, I'm going to undo this in just a second, is that there's really a second linear factor of x minus 1 right there. So that means that we have 4 linear factors right here. And I'm expecting this thing normally to cross the x-axis 4 times. But with multiplicity, that throws a little wrinkle in that expectation. So let's take a look. All right, when you're asking yourself, what's my 0, you're really looking at a linear factor like x, and you're saying, okay, what value of x would make this equal 0? Well, x would equal 0 if x was 0. So that's the first multiplicity you get. Excuse me, the first 0 you get. And when we ask about the multiplicity, it's basically a question of exponents. That x doesn't have an exponent on it, which really is an exponent of 1. So the multiplicity of that 0 is 1. It only occurs 1 time. Now let's move on to the second linear factor. X minus 2 would equal 0 if x were negative 2. Think about that. Negative 2 plus 2 would equal 0. And that factor also only occurs 1 time, so that also has a multiplicity of 1. But now, the last factor that's listed, x minus 1. X minus 1 would equal 0 if x were 1. 1 minus 1 would be 0. But because there's an exponent of 2 right there, that's the multiplicity of that second 0. And now that we know a little bit about this graph, where its zeros are and what the multiplicity is in each of those cases, let's draw ourselves again a relatively quick graph, and let's see what's going on. Boy, everything is pretty close here. I've got to go to negative 2, 0, and positive 1, and that's really it. So let me go blue here, and let's see if we can graph this. This thing has a 0, which means it touches the x-axis at 0. It happens again at negative 2, and it happens again at positive 1. So I used those 3 numbers to come up with my x-intercepts. All right. Another thing I want to think about right here, and we can really do this kind of now or later, is we want to talk about the end behavior, because nothing that we're learning right here is replacing things that we have learned before. Now, if I were to go back and write this polynomial in expanded form, that'd be kind of a lot of work, and I'm not going to do the whole thing, but let's just look at our leading term. X times x squared. Oh boy. X times x squared. Well, x times x would be x squared times another x squared would be a positive x to the 4th. And again, there's other stuff at the end, but this term is really all we care about for end behavior. And when you put a negative number into x to the 4th, a negative number to the 4th is positive. So this thing is going to go up on the left-hand side. On the right side, when you put in a positive number and to the 4th power, it becomes positive as well. So this graph, everybody, is going to go up on the left-hand side, and it's also going to go up on the right-hand side. Because again, what we learned about end behavior before is still applicable. But if you don't know what you're doing here, you can run into a mess on this function. You might come down and then back up and then back down, but then you get this weird sharp turn right there, and that's not really what happens in this case, although it's actually closer than you might think. Let's think about how multiplicity impacts our graph. So let me go back a slide. Right here, if your multiplicity is odd, such as 1, the graph crosses the x-axis at that 0. That's what happens with an odd multiplicity, which we have here and here. So at both 0 and negative 2, with a multiplicity of 1, the graph has to cross the x-axis. And I love where I put that, so let me move that there. So that means that at negative 2, we are crossing the x-axis and coming down below it, and then we've got to come back up to this spot right here. That happened, so that was a multiplicity of 1 at negative 2, and also at 0, there's a multiplicity of 1, so the graph has to cross again up above. But now here's the interesting part. At x equals 1, we have a multiplicity of 2. And with an even multiplicity, the graph doesn't cross the x-axis. It bounces off it at that spot. So what that would look like, everybody, is something like this. It kind of goes boing like that, and we get not this sharp V. That's not really the way polynomial functions work, but kind of a smooth little transition looking like that. And my graph is a little bit small here for you to see that, but that's effectively what happens here. So we talked about earlier how a fourth degree function can have a maximum number of x-intercepts of 4. This one, though, you'll see, only has 3. And just to show you guys I'm not making stuff up, I'm on my iPad right now, and I've got the Desmos app on here. Desmos is a free online graphing calculator you guys can use. And if we were to graph this function in factored form, this was x, and then multiplied by, I've forgotten it already, multiplied by x plus 2, and then x minus 1 squared. So x plus 2, close that, and then in parentheses we had an x minus 1, close the parenthesis, and square it. Okay, and now very, very quickly, Desmos just showed us what this looked like right here, and I think we can see pretty quickly here, guys, that this graph does effectively what we thought it should do. Right here at -2, it crossed through the x-axis. It did the same thing at 0, but then right there at 1, 0, it bounced off the x-axis. We'll zoom in on that a little bit. It bounced off the x-axis, but it did not cross it. So that's exactly what we thought was going to happen here. Their graph obviously is a little bit prettier than ours, but we're not trying to be super specific with this. All right, guys. So I wanted to do another example like that with you, and this one's harder because the function was given to you in standard form. We've got to put it in factored form, and that's going to happen in a lot of these cases here. So what are we going to do first to factor g of x? We're going to look for a greatest common factor, and it doesn't look like we can pull out any constant because of that 1 up in front, but I do think we can pull out, let's see, we've got 4x's, 3x's, 2x's. We can pull out an x squared. And while we're at it, I'm going to go ahead and pull out the negative with it. Okay, when we pull out a negative x squared, that's going to turn this into a positive x squared. And everybody likes factoring better, which we're going to have to do next, when the leading coefficient is positive. Second term was 2x cubed. We pulled out a negative, so this now becomes -2, and there were 3x's. We pulled out 2, so there's just 1 left. And the last term, plus 15x squared, pulling out the negative makes that a minus. The 15 stays. There were 2x's. We pulled both of them out, so that's where that one ends. And now that we've pulled out a GCF, we want to try to do some normal reverse FOIL factoring on this quadratic trinomial that's left over. What times what is going to give us x squared? Just an x and an x. I'm looking at this 15, which is negative, so that means my signs are opposites, 1 plus and 1 minus, and now we need two numbers that multiply to -15 and combine to a -2. That, I'm hoping you guys see that quickly, is a -5 and a +3. So you're welcome to check that with FOIL and make sure it works, but I feel pretty good about that. Now, since we have it in fully factored form, we can figure out our zeros. What value of x would make this equal 0? That's going to be 0. What value of x would make x plus 3 equal 0? That would be a -3. And what value of x would make x minus 5 equal 0? That's a +5. Okay, so we've got that, and now let's talk about multiplicity. This 0 right here, which was 0, has an exponent of 2, so that's your multiplicity. It occurs twice. -3 came from this factor, which just has an exponent of 1, as does the x minus 5, so each of these next two zeros has a multiplicity of 1. Okay, so we're making good progress. Now let's see what we can do to come up with our graph here. Let's see, I need a 0 at -3, way out here to the left, and then even farther to the right, I need a 0 at 5. And these three x values that we've come up with here are zeros. Those are the x-intercepts. One right here at -3, one at 0, and one at 5. Got it. What else? Let's talk about end behavior, which is even easier now when the function is already in expanded or standard form. So our end behavior, we're dealing with a negative x to the fourth. So when you put in a negative number for x to the fourth power, a negative to the fourth is going to be positive, but the opposite of that pulls it negative. So we are going down on the left. And then on the right, when we put in a positive number, positive to the fourth is positive, but taking the opposite of that pulls us down on the right as well. So I know that this graph is going down on the left, and it's also going down on the right. What happens right here, guys, at this 0 of -3? Since the multiplicity is 1, which is odd, we know the graph goes through the x-axis and then has to come back down to this spot right here, where we have a 0 of 0, but with a multiplicity of 2, which is even. So what's going to happen there, guys, is that the graph isn't going to cross the x-axis at 0, but it's going to bounce off it and then go right back up above it yet again. And the last one we have to consider is 5, where the multiplicity is 1. That's odd, so that means that the graph is going to cross through the x-axis there and continue on down into the fourth quadrant. So again, you guys, we're just coming up with rough sketches right here. These are not super accurate graphs, but that's more or less what this graph looks like. Okay, hopefully not too bad. And the last thing we have to talk about, we're going to just discuss real quick. It's really just a vocab issue here, guys, of something called a relative maximum and a relative minimum. And a relative maximum, well, the word maximum means the highest point on a graph. However, if you look at this cubic function that I've drawn here, there isn't really a highest function on this graph because there's an arrow on the left and this thing continues to always go higher and higher and higher to the left. However, what's going on, guys, at this point, hang on just a second, sorry, at this point right over here is that point is the highest point in its neighborhood, either immediately to the left or immediately to the right. This graph goes down on both sides. So this point right here is what we call a relative max. It's higher than any other points around it in either direction. And then we've got a relative minimum, which occurs at this point right here. It's not the lowest point on the entire graph because there are points here and here and here that are going to be lower than that. But this point right here is a relative minimum because it's lower than the points immediately around it on either side. Okay, so that's what we mean by a relative min and a relative max. And all we're going to do with this section, guys, is we're going to use our graphing calculators in order to find a relative max and a relative min for you. And Desmos will do that for you automatically, but that doesn't help you guys. So I'm going to show you guys how to do that on your TI-84 the next time we're together in class. So let's not worry too much about relative max and relative mins right now. We'll polish that one off tomorrow. Okay, guys, thanks for sticking with me. That's a wrap then on section 5.2. Good luck.